Hi, we're the Galaxy Classification Redshift Wrangler team. I'm Connor Wolff.
I'm Cassius Bermudez.
I'm Lorelai Lovell.
I'm Perez. The primary focus of our research was centered around the evolution of galaxies over time. We hypothesized that irregular galaxies were more common closest to the time of early galaxy formation. This is because galaxies were closer together and therefore interacted more often. To study the older galaxies, we analyzed the data from the Redshift Wrangler citizen science website to calculate galaxies redshift and record galaxy type. We additionally used data from the SDSS catalog to study younger galaxies. Redshift is a phenomenon that occurs when looking at an object that is moving away from us. The light coming from most galaxies elongates, which means that it's moving toward the red side of the spectrum. By observing the redshift of galaxies throughout the universe, we can see that they are moving away from our own galaxy. Hubble was the first to observe this. The light he was able to capture and analyze appeared to be redshifted. This observation led us to believe that the universe is expanding. Higher redshift typically indicates older age in an object, while a lower redshift indicates a younger age. On this slide, we have Hubble's diagram. It describes distance versus redshift. The data comes from a supernova survey conducted by Hubble. Objects plotted on the right side have a higher redshift, which indicates an older object. This is the first observational evidence we have ever had of a rapidly expanding universe. The first line of the graph of the universe represents 30% matter and 70% of some mysterious substance, which we call dark energy. The second line demonstrates a universe where there is 30% matter and nothing else. This one is quite difficult to interpret because there's nothing within the other 70%. Yet what is interesting about that is it still fits the data better than the next line. This third line shows that it would look like what it would look like if the entire universe was solely made of matter and had no dark energy. The fact that the first line, the one with 70% dark energy, fits the data better than the other two leads us to believe that there's something causing the expansion of the universe, which we now call dark energy.
Galaxies are classified into many categories, including giant elliptical, dwarf elliptical, spiral, barred spiral, and irregular. When looking at the data, we classified the galaxies into these categories to find the evolution of them by observing their redshifts. This allows us to observe the types of galaxies we think formed in the early stages of the universe. However, due to many of these objects being over 10 billion years old and lack of resolution from the Hubble telescope because of distance, it often becomes difficult to determine the shape of many of these galaxies.
Quasar is derived from the word quasi-stellar, which means star-like. This is because when first photographed in the 1950s, they looked faint and had the resemblance of stars. However, this star presented scientists with some confusion. It had a redshift of 0.158, which at the time was massive and very hard to believe. If this was true, it would mean that quasars are so bright that they outshine all stars and the Andromeda Galaxy. Now we know that this is true, and quasars are associated with galaxies in the nucleus.
Hydrogen emits and absorbs light at certain wavelengths as the electron jumps into shells of different distances from the nucleus. The spectrum of emitted and absorbed light can be seen on the right. The lines in the spectra represent the specific wavelengths at which hydrogen emits and absorbs. Since this property of hydrogen is constant throughout the universe, we can use these lines to gain information even about the most distant galaxies.
We took 30 galaxies from the Redshift Wrangler citizen science and identified their emission lines, which are boxed in red, and absorption lines, which are boxed in blue. Since we know the original hydrogen emission lines and where the observed emission lines are, we determined how shifted the light was using the equation on the right.
To find high redshift galaxies, we used the Redshift Wrangler Citizen Science Project to analyze galaxies that were photographed by the Hubble Space Telescope and used spectra collected from the Keck Observatory. We used the two plates from the SDSS, which also had galaxies that had a redshift of up to 9.
As seen in the figure, we found that irregular galaxies as a percentage of total galaxies were most common at higher redshifts, but their frequency dropped at very high redshifts. We had very few data points in that range, so that might explain this effect. Elliptical galaxies, both dwarf and giant ones, were more common at lower redshifts. Giant elliptical galaxies are believed to form due to galactic collisions between irregular and spiral galaxies, which can be explained with our results, as giant elliptical galaxies may not have had time to form in the early universe. Quasars, both by percentage and by number, were more common at higher redshifts, especially redshifts near z is equal to 3. This finding is likely due to the fact that quasars are especially bright, which means they're easy to find even when they're very distant, and the fact that the younger universe had more available gas to fuel more quasars. Correlating galaxy type with redshift confirms that irregular galaxies and quasars were more common in the early history of the universe. Future studies from the James Webb Space Telescope could provide more data for very distant galaxies and quasars to improve statistics at high redshifts.
SEAS was a great opportunity for me, and my favorite part was going to the Johnson Space Center and seeing the mock-up of the ISS in the Neutral Buoyancy Lab.
I'm incredibly grateful for the opportunity to have participated in the SEAS internship, where I was able to gain invaluable experience and learn from some of the brightest minds in the field of STEM. The work we have done helped me to grow in a hands-on environment, which is something I don't get often in a classroom setting.
SEAS has helped me learn new important topics in relation to STEM, and I'm glad to have this opportunity. It also allowed me to create new friendships, and I'm happy that I learned what Redshift really is.
SEAS had been a once-in-a-lifetime experience that allowed me to explore my interest in science and meet truly incredible people.
Here are some pictures of our time at SEAS. We would like to thank Dr. Rees for teaching us all of her knowledge about astronomy and redshift. We would like to thank Bob Twiggs for his incredible generosity in letting us use his Z-cubes. We would like to thank Dan Tanney and all the other presenters for teaching us about what they do in the STEM field. And lastly, we would like to thank Miss Margaret and Miss Selena for making everything work at SEAS.